In this stats review, we're going to first look at independent versus dependent. Well, dependent samples occur when you have two samples that affect one another. So in this illustration up over here, you'll see, like lines going back and forth showing that there's a relationship between the two populations. They affect one another. Where independent over here, what happens with these two samples do not affect one another. They're separate. So in this example, classify the two given samples as independent versus dependent. Well, sample one, if we look here, we have the number of hours 49 kids spend talking on a cell phone each week. And now sample two, the number of 38 adults spend talking on a cell phone each week. So we have two separate samples. We're looking at kids and we're looking at adults. Just the number of hours they're spending talking each week on cell phones. And so we have these two samples. They're different. They're independent from one another. All right. So again, we have kids, we have adults. They don't really affect one another. Now, I know some parents out there will probably say, well, my kids, their cell phone, I restrict their use. So it really depends on what I say. Well, in these types of samples, in this type of research, we're just looking at kids, and they might not be your kids. These kids might not be related to these adults at all. So we're just going to look at what these type of things say. The number of kids here are 49 kids, number of adults 38. Just looking at how much they spend talking on the cell phone each week. They're independent samples. They don't affect one another. Now in this example, the two given samples, are they independent or dependent? This one here, we have sample one, we have 33 oranges from California, 37 oranges from Florida. So we have oranges from two separate states. These two samples are going to be independent of one another. They're not going to affect one another at all. No relationship between the two. All right, so that's independent versus dependent. So let's go on and do some more examples. We're going to jump right into an example here. Test a claim about the difference between two population means. So the first thing we want to do is we're going to try to identify the null and alternative hypothesis. All right, so for the given data, all right, so find a test statistic, find a standardized test statistic, and decide whether the standardized test is in the rejection region. All right, so the samples are random and independent. All right, so random, independent. Those are two keys right there. All right, so we have all this information here. We have a claim of, so that's our claim. And if we notice here, there's no equal to sign. So that right there is actually going to be our alternative hypothesis. So let's get that down right away here. So we know our alternative, it's given right there in our claim. So we have the mu less than the second one. So we got the first population, and let's write that a little nicer. So we have the first population and the second population. So we're looking at the two population means. So that's why we have 1 and 2 there. So the claim, that's our claim, so which means that our null is going to be the opposite of that. So remember, the alternative and nulls are the opposite. And so over here we have is going to be greater than or equal to that second population mean. So that's our null, that's our alternative. And let's keep going here. Next, we're going to look at the test statistic. So we're going to have to, let's get a highlighter here. We're going to look at the x bar 1 right here. And let's see here, x bar 2. So we're going to have to subtract those two. All right, let's get a pen. So we're going to have to do 12, 20. Oh, we're going to have to improve my penmanship here a little bit here. 10, that's the 1220 minus 1200. And that equals 20. Now we're going to use our formulas here for, now this is dealing with two means, now our two populations, two samples. So now we're going to use these formulas, and let's keep going. So first we need to calculate that standard error. So we need to get this part first, that standard error first. So let's plug in some values and let's get that. So this part here is going to be root, and then we have 80 squared. Now where did I get the 80 from? The 80 is given right up here. And that's going to be over N1. N1 is 35. So 35. And that's going to be plus, all right, this one here, 120. So that's 120 squared over N2, which is 55. So 55. All right, so let's get what that is there, and that will get us our denominator to get our test statistic. All right, so let's calculate that real quick. So we're going to use this TI-83 calculator. Now, I do have this available for you guys to download. I'm pretty sure it only works on Windows computers, but there's all sorts of calculators online, or you may have one handy as well. Let's go through a second, and we're going to group in symbols. 80 squared divide by 35, group in symbol, plus 120 squared divide by 55. And there we go. So it's about 21.0873. So about 21.0873. All right, so that's just this bottom part here. Well, the top part's not very complicated. We're just basically subtracting there, but that's the bottom part. And so now this is where we come across an assumption that's made. The null hypothesis basically assumes that those means are equal. So, or greater than equal, but equal. But in essence, this part right here, when subtracting, if they are equal, this would be 0. So again, that would be a 0. So our test statistic is really just going to be looking at this part here, and we have that, which is 20. That's going to be divided by this 21.0873. So that's all we're going to end up doing here. So 20 divided by that piece there. And we'll go right back over here. So it's 20 divided by the 21.0873. So approximately, all right, so we're in here. So approximately 0.95, so about 0.95. So the Z test statistic is approximately, I like to put approximately, 0.95. 0.95, and in most Z tables, they usually don't go past 2 decimal points. So 0.95. So now we got to take a look at our alpha. So we have that Z. So now we have our test statistic, and we now need to go looking for that rejection region. So alpha 0.01, 0.01. But we need to recognize that this is a greater than or equal to, meaning one-tailed, So let's go to our Z table, and we're going to need to look for 0.01 as that alpha value. Now again, this is looking at greater than or equal to. So is this what is left or right tail? Let's review that real quick. One thing to look at that kind of gives it away is the alternative. So looking at this alternative hypothesis here, we have less than. So that gives it away. We have a left tail test. So we're going to look at that negative Z values. And let's get a Z table up. Here we go. And we are looking for 0.01. So 0.01. All right, so let's focus in here. Oh, here we go. So 0.017429. So with the statistics here, with what we're doing, we're going to basically, it's in between here somewhere. But for our sake, we're not going to do exact. We're going to pick the one that's closest. And the one that's closest is right here. And so we're at negative 2.33. Negative 2.33. So we're going to compare, is this 0.95 in the rejection region? So that is going to be negative 2.33 is what we said there. And that's going to be that critical value. So is this in that rejection region or not? The answer is no. it's not in the rejection region. If the standardized test statistic lies in the rejection region, we reject the null hypothesis. Otherwise, we fail to reject the null. So in this instance, we are failing to reject the null. We're failing to reject the null. All right, so at a 1% significant level, because that's 1% up here, again, there is not enough evidence to support the claim. Now, remember, not enough to support the claim. What do I mean by that? Well, remember, the claim, and let's zoom in on there. Remember, the claim here in this instance was actually the alternative. So the claim was actually the alternative this time. And so in this situation, there's not enough evidence to support the claim. Key claim was the alternative there. So at a 1% significance level, there's not enough to support that claim again. I'm just going to repeat that because sometimes it takes a little while for that to sink in. It's a little odd, but the claim is a little different here. The claim is that alternative. So now this example, we're looking at confidence intervals. So to construct a confidence interval for the difference between two population means, we're going to use this formula here. Now this looks crazy and a little complex. Do not be afraid. Each one of these individual pieces are pretty easy to get, and most often some of them are given. And basically, we're just plugging in values, and then we're going to solve. That's all this is. So do not be afraid of these weird, crazy, fancy formulas. The other part I'd like to point out is if you notice in this formula here, we have this z here for the confidence interval, and we have these values here. These are identical to this. So once you get this, you have that value on both sides. Okay? And at the same time, if you take a look here, we also have the x1 minus x2. That's the same on both sides. So the only difference is we're finding this x1 minus x2, we're subtracting to get the lower bound, and then over here we're adding to get that upper bound of that confidence interval. And that's the only difference. And most often than not, we're given many of these values. So again, this value is the same here. So we have these values are the same. Okay. So let's highlight, let's put it there. So this is here, is the same here. And that's the same here. So once you start breaking this down, you start realizing, wow, this is actually much easier than it looks. We're really just calculating these values once, and on one side subtract, on the other side we're adding. So let's go through and fill this out. So the first thing I see, all right, so we have 95% confidence interval. All right, and one other thing is you notice here we have two sides here. So first, 95% confidence interval, we're going to do 1 minus 0.95, and that is 0.05. Now that should be looking familiar. That looks kind of like the alpha values we usually are looking at, 0.05. And so we have this 0.05. All right, looks like here, again, just want to emphasize two sides, two-tailed. So we're going to take that 0.05, and then we're going to divide that by 2. So 0.05, divide by 2, and we get 0.025. Now, by now, some of you guys are probably, will knee-jerk and say, oh, I know the z values that are going to be there. That's pretty simple. Some of you guys might not remember it right away, and that's okay. We can start memorizing some of the key ones here. And some of the key ones we normally see are that 0.05, 0.025. But let's go to that z table. In the z table, we're looking for 0.025. Oh, right here, 0.025. And that is at negative 1.96. Now remember, standard normal curve, symmetrical. Negative 1.96, positive 1.96. And now you start to see what we mean by that confidence interval. So over here, it's minus or negative 1.96 goes here. So minus 1.96 and the positive 1.96. Again, minus 1.96, positive 1.96. And so that's, you can hopefully start seeing how this is kind of tying in. So over here, we know it's going to be 1.96. That's going to be plugged in there. And it's already subtraction, so we have the negative already in there for us. And over here, it's going to be a positive 0.196. All right, let's make sure and verify one more time. So negative 1.9 right there, 6, and we're good. All right, now I'm gonna put this all on one line here in formula just so we can see it as well. But we're gonna get the individual pieces first. Now, if we notice over here, the sigma here, sigma 1, sigma 2, a lot of values are given to us. So we just really need to plug it in. So let's go ahead and plug it in. I'm going to erase a little bit of this here, and we're going to plug these values in. So here we inputted them into this part here, that square root part. So we have the sigma squared 1 right here, and sigma squared 2 right here. Now, 45, 41. One of the keys is they both have to be above 30. So N1 and N2 are both above 30. I just want to make sure we circle that right there. They both are above 30, so we're good. And so we can put this right in our handy dandy calculator and get a calculation for this. So let's do that real quick. Okay, so here in the calculator I inputted what's in here. We got the root 9255 squared divided by 45 plus the 9270 divided by that squared divided by 41. Got my group and symbols in there. Enter. There we go. So now that's this portion. That's the part that's in the square root. So let's write that down there. So this is 1 point. X. That's 1999.842341. All right, so that's the part that goes in. That's the part that's in those square roots. That's all done. That's done for us. Now the next part, we have the z there. Okay, so we're basically going to times that by the z value, 1.96. So times 1.96. So for our confidence interval, the part that we're going to subtract and add is right there, 3,919.69. So that's going to be the part, that's this part right here. That's all this ugly mess here is right there. All right, so let's clean this up. I'm going to write that number down and let's put this in that formula. All right, so here we go. I would type it out a little nicer so my handwriting wasn't too distracting. But what we have here is this x1 minus x2 right there. x1, x2. So that's where those values came from. And again, this value here came from all the calculations that we did for that square root. And then we multiplied it by the 1.96, the z. So all that stuff was taken care of. All right. So now we're at a point where we just simply have to get this value here, subtract it, get that value there, same value as above. And, oh, we got one mistake in here. Let's make sure we correct that. It's a very easy mistake to do. Let's grab this row here quick. If we look in here, that was supposed to be minus. Over here, there we go. That's better. All right, so we have the same values up in here. We're supposed to be subtracting those x1 minus x2. There we go. Over here, we subtract that value we got, and then we add the value we got. All right, let's just get that, and then we have our interval. So subtracting those, we end up with 17,140. So again, same calculation on both sides. And now we're just going to subtract and we're going to add. So from this value here, we're going to subtract the 39.9.69. And it's approximately 13,220. So over here on the top, it's approximately 13,220. Now, instead of subtracting, we're going to add. So we have 17,140. Now this time we're adding 3919.69. And that's now approximately, we'll probably round that up there, 21,000 60. Now it depends on what the directions say. It might say the nearest whole number, it might say nearest tenth. These numbers are so large, that's why I'm doing to the nearest whole number. So 21,060. So just make sure you follow the directions of how it says to round. All right, so I know I did it in bits and pieces, but sometimes it's easier to do that. First thing we did was we got this square root, then we multiplied it by the z value we got. After that, we found the x1 minus x2 and we subtracted and then added the values from there. So now we have our interval. So here it is, 13,220 up to 21,060. And let's see if we can get that in here typed up nicely for you. And there we go. So the 95% confidence interval for the mu1 minus mu2 is shown below. And there we go. I have it shown below for you. So it's that 13,220. It's less than the subtraction of the means from the two populations, or two samples, and is going to be less than 2160. So there's our confidence interval. So what exactly does that confidence interval mean? So what this means here is that, say we take, all right, for example, say 100 different samples, and we compute a 95% confidence for each sample. What we're saying is approximately 95 out of 100 confidence intervals will contain the true mean, the true population mean. So that's what this means. So this means that 95%, basically there's a 95% chance that the intervals, the confidence intervals, will contain the true mean. So again, let's say it again. So for example, we have 100 different samples. That means 95 out of 100 will contain the true mean. Approximately 95 out of 100 will contain the true mean. All right, let's keep going here. So now we're going to look at the t-distribution, two-sample t-distribution, or two-sample t-test. So the first thing here we're going to do is we're going to find the critical values. Now this is again assuming that the population variances are equal. Assuming the population variances are equal. So we're going to begin by finding the degrees of freedom. For this, it's going to be a little different. The degrees of freedom are going to be n1 plus n2 minus 2. So let's get that real quick. So n1, we have those values right here. So 12 plus 10, so we have 12 plus 10 is 22. So 22 minus 2. So our degrees of freedom are going to be 20. So we have degrees of freedom of 20. So the next question, is this going to be left-tailed, right-tailed? So before we said that the alternative, we are given the alternative here. The alternative normally gives it away. So this one does give it away. We have less than here, less than. And that kind of points in the direction of the left. We have a left-tailed test here. So again, alternative hypothesis kind of gives away if it's left-tail or right-tail. And if it says less than, it's going to be left. It says greater than, it's going to be right. It says not equal to, two-tail. This one, left-tail. So we're going to look at the t-table here. T-table, and we're looking at one tail. So right over here, one tail. And if we remember, let's go back and double check here. We have 0.005, 0.005. So 0.005, degrees of freedom of 20. And so the value on the table is 2.845. So 2.845. So 2.845. But now remember, these distributions are symmetrical, and we're dealing with the left tail. And so there's not going to be positive 2.845. It's going to be the negative because we're dealing with left tail. So that there is going to be our value. All right, so that's the critical value, assuming, now here we go, that was assuming that the population variances were equal. Now let's take a look at the same exact values, same everything, except this time we're going to go in from a perspective of the variances are not equal. So this one again, we were looking at if the variances were equal. Now we're going to look at variances not equal. So now variances not equal, begin by finding degrees of freedom again, but this time the degrees of freedom, we're going to look at the minimum of n1 minus 1 and n1 minus 2, where n1 again and n2 are the sample sizes. So what would be the minimum there? So we take the 12, let's get the pen. So we have 12 minus 1, and that's going to reverse 10 minus 1. Obviously, this one here is going to be smaller, 10 minus 1. So the degrees of freedom here are going to be, so degrees of freedom are going to be 9. Okay, so now we have degrees of freedom of 9, but we have the same situation. So on our t-table here, going to the t-table, we're in the same column, the point 0, 0, 5. This time we have degrees of freedom of 9, so we're looking right there. There we go. So 3.25, 3.25. So we're looking at 3.25. But once again here, that's the t-value. It's still a symmetrical curve. And we're dealing with left tail, so it's not going to be just 3.25, it's going to be negative 3.25. So this here is going to be our critical value if we do not have, if the population variances are not equal. So we do have a difference here. The top one here, we did it as if we are assuming that the population variances are equal. The bottom one, we did as if the population variances are not equal. So equal versus not equal. So there will end up being a difference in those critical, the critical values in the rejection regions. So here we are going to we're going to test a claim about the difference between two population means. All right, so we have an example. A pet association claims, oh, there's a keyword there. Let's highlight that, claims. We have claims that the mean annual cost of food for dogs and cats are the same. Oh, there we go, same. So claim that something is the same. That should cue us in on what the claim is and what the null and alternative hypothesis should be. So the results for the samples of the two types of pets are shown below. So here we go, shown below. We have an alpha of 0.1. Can we reject the Pets Association's claim? Assume the population variances are, oh, here we go, key here. Population variances are not equal. So when we get the degrees of freedom, it's going to be a little different. It's not going to be the n1 plus n2 minus. We're going to look at the minimum of the n1 minus n1. We'll go over that in a second, but there we go. We got the population variances are not equal. Assume the samples are random. Okay, good. And independent. Good. And that they are normally distributed. All right, so that we can proceed with the t-test here because of the assumptions that we're going to make here. All right, so let's go to it. So again, just making sure we emphasize this, the claim. The claim is right here. Well, let's get this off the screen here. The claim is the mean annual cost of food for dogs and cats is the same. So that's the claim. The claim is that they're equal. The claim is that they're equal. And so what that means is that our mu1 equals mu2, it means that this is going to be our null. That's going to be our null hypothesis. So we're testing the null hypothesis if they're equal. So our null is actually our claim here in this situation. And the alternative is going to be the opposite of that. It's going to be not equal to. So alternative is going to be that they are not equal. So alternative is the opposite, not equal. Okay, here we go. And now degrees of freedom. So we clean it up a little bit, make it a little nicer for you. So now degrees of freedom. If we look here, because variances are not equal, we're going to take the minimum of n1 minus 1 or n2 minus 1. Well, And 1 minus 1, that would be 17. And 2 minus 1 would be 7. So our degrees of freedom, will be 7. All right, degrees of freedom 7. Now let's take a look here. Next thing is we have equal to versus not equal to. So we have, the question is one-tailed, left-tailed, right-tailed, or two-tailed. This one here, equal to, not equal to, we have two-tailed. And so that tells us to go to our alpha value of 0.1. And so that's going to be alpha divided by 2. And that's going to be 0.05. 0.05. Right. So this value here, now keep in mind, sometimes when you go to the tables, we have to make sure we pay a little closer attention, especially for the t-tables. Now this here is very valuable if you're using some type of technology, say like the calculator. Now if we go to, so on this t-table, we have one tail versus two tail. Now it says two tails, so if we have a two tail and it's 0.1, it's given to us, there it is. So we're good. Now if we're using technology, you want to be more careful of what that alpha value is. So we are actually given, hey, look, it's a two tail, we have alpha of 0.1, our value is right down here, bam, 1.895. 1.895, okay? So again, on the t-tables, it gives you the information a little more direct. So two tails, we're given an alpha value of 0.1. That's how we got that. Some students will make the mistake of saying, hey, all right, two tail, I calculate the alpha, it's 0.05, 2.365. All right, we have to be careful here. So two tail, it gives us the alpha value of 0.1. It actually calculates it and has it divided already out for us right there, 1.895. Okay. All right, let's keep moving. So our rejection regions are if that t-value we get is going to be less than a negative 0.895 or greater than. Remember, we have two-tail. Remember, we're on two-tail. All right. Now we got to get the test statistic. So we have to plug in some values here, and we're going to test it and see if it falls in the critical region. And a lot of the values, again, are given to us right up over here. And if we're assuming that they're equal, this piece right here, we're going to assume is 0. So very similar to what we did before. So we have to get this value down here, which is in this formula. So we're going to do the S1 divided by the N1 plus, or excuse me, make sure we square it, the S2 squared divided by the sample size of that one, N2. And we're going to take the square root of that. So let's put that in the calculator here. Okay, so here we go. We have our 42 squared divided by that N1 with the S2 squared divided by the N2. And we have our grouper symbols. We're going to hit enter. There we go. Now we need the x1 minus x2. So that's going to be the 228 minus the 193. All right, so it's 35 divided by this mess here. So divide by, well, here, let's make sure you know what I'm doing here. So 35 divided by 16, and we'll just do 0.688. Enter. So we have approximately 2.097. So after we do this and plug it in the formula, our test statistic we end up getting is 2.097. So 2.097. So what that means is, since this is 2.097, it is greater than the 1.895. Since it's greater than, we're going to actually reject the null, since the test statistic is within that rejection region. But what does this mean in the context of the problem? So what does it mean? Okay, so we have to remember what the claim was. The claim was that they're equal to, the claim was the null. All right, so since the null hypothesis is the claim, all right, when we reject the null hypothesis, what we're going to say is at that 10% significance level, there is enough evidence to reject the claim that the mean annual cost of food for dogs and cats are equal. So we're rejecting the claim that the mean annual cost of food for dogs and cats are equal. So we're rejecting that claim. Remember, that claim was the null. And so that's how we interpret it in terms of the context of the problem. So now we're going to move into testing the claim about the differences for a population of paired data. Now, paired data. How do we know this is paired data? Well, we have patients, and we have each of these patients, and we measured, so in this particular example, we measured headache hours before and after. So before and after something. So let's take a look. The table below shows the number of hours per day 11 patients suffer from headaches before and after 7 weeks of soft tissue therapy. So again, we're dealing with a single patient, looking at the data for that patient before and after. And that's what we're looking at, so of each individual patient. So this data is paired and linked to one another here. So we want to we want to identify the claim. So identify the claim. So let's try to highlight that here. So well, let's move this down a little bit so we can see better. All right, so here we go. Does the therapy help to reduce the length of time? So there's our claim. So reduce the length of time. That's going to be our claim. Okay, so like we said, the key was to reduce the length. So we're going to test to see if the daily headache hours after the therapy is significantly less than their daily headache hours before. So that's what we're looking at here. Is it significantly less? So is that 2.9 significantly less than 1.8? Oh, but we notice here this one's actually more. So we're going to look at, now that's an isolated example, but we're going to look at the sample as a whole. So that's what we're going to do with this paired data. So let's go and take it step by step. So let's start with the null and alternative hypothesis here. So null, I'm just going to draw this out here this time, make it a little quicker. So the H null is going to be, the UD is going to be less than or equal to 0. And the alternative here is going to be if that is going to be greater than 0. So greater than 0. So null versus alternative. We're looking at less than. So is this claim, looking at the claim, is this less than, significantly less than the before? So that's what we're going to look at. So next step, degrees of freedom. Next step, degrees of freedom. So we have 10 in our sample, so that's going to be pretty simple. So it's going to be 11 minus 1. And so we're at a degrees of freedom of 10. So now, is this left tail, right tail, two tail? And remember, the alternative hypothesis normally gives it away. So if the alternative here is greater than, that typically means that we are right-tailed. So we're right-tailed on this one. Now again, if you use technology, that's perfectly fine, or you can use the table like I'm going to do right now. So as we use the table, we are looking at, well, let's see here, alpha of 0.01. Now again, this is one tail. So when we go to the t-table here, well, the reason why we're using t-table, sample is pretty small. So we're doing a test where our test is a t-test here. All right, so we're dealing with one tail. Now remember, the two tail, it actually calculates that for us in these tables here. That's why we didn't have to really do anything with the alpha divided by 2. This one here, again, we're on this column here, one tail, and we're at 0.01, so right here. We had a degrees of freedom of 10, so right here we go. So 2.764, 2.764. So 2.764, this is going to be, help indicate our critical region. So what this means is that right tail, we're looking at to see if the statistic that we're going to get is going to be greater than that. So question is going to be t going to be greater than the 2.764. So that's the question that we're going to try to answer. Is it going to be greater than that? All right, so let's check it out and see. So for this question, rather than the calculator or doing everything by hand, I would actually try to use Excel. So I'm going to put this data in Excel. Here it is. So the data is here in Excel. Let's get that in the window a little better. There we go. So we can see the buttons that we're going to press. There we go. Now, here in Excel, we're going to go to the Data tab, Data Analysis. In Data Analysis, we see t-test, pair to sample for means. There we go. All right, so let me start over here. First thing we're going to do is, in variable 1, highlight. Variable 2, we're going to highlight. Alpha level 0.05. Oh, let's double check to see what that said in the problem. In the problem, it said 0.01. All right. And so in output, I'm going to click, and if I just click any of these cells here, that's just basically where it's going to put the output. And okay, and here we go. Let's see here. Let's get some of this data, and let's make sure we understand what this says. All right, so we're looking at here. There's our t statistic right there, 2.57, 2.57. All right, so 2.57. So what exactly does that mean? Is 2.57 greater than the 2.764? The answer is no, it's not. So the 2.57 is not in that critical region. So since it's not in the critical region, we are going to fail to reject the null hypothesis. So we're going to fail to reject the null hypothesis. So what exactly does that mean? All right, so let's try to put it in words here. So that is 1%. So at the 1% significance level, there is not enough evidence that the soft tissue therapy helps to reduce the length of time patients suffer from headaches. So again, at the 1% significance level, there is not enough evidence that the soft tissue therapy helps to reduce the length of time patients suffer from headaches. Okay, well, let me type that out and put it up on that screen for you. So let's make sure we know what just happened there. So the difference here, so this here is the null is if it's less than or equal to 0, the difference is less than or equal to 0. The alternative is if that difference is greater than 0. So what we determine here is that we are accepting the null, which means that the difference is less than or equal to 0, meaning that no difference. That's what we're accepting here. Now, if the alternative was true, we were looking at the difference is greater than 0, so it did actually reduce the time for the headaches. But since we did not reject the null, at the 1% significance level, there is not enough evidence that the soft tissue therapy helps to reduce the length of time patients suffer from headaches. Okay. So this next one, we're going to construct a 90% confidence interval. Now, this one here for paired data can get kind of messy. So let's take a look at that paired data for this particular example. So here's the paired data. Now, what I'm going to do is we're going to get each of these individual little pieces here. And as we get each of these little individual pieces here, we're going to actually use Excel. Because you see these little summation symbols, we're going to sum quite a few of these differences. So see the D's, those are all differences. And so instead of doing this all by hand, we're going to get this in Excel, and we're going to have Excel subtract them. And so that's going to be the D. And then we're going to summation the differences. That's what that means, sum the differences. And so we're going to let Excel get the differences, sum them for us. Now you see D squared. That's the summation of the differences squared. So then this part here is going to be the differences added up. This one here is going to be, we're going to take the differences, square them, and then sum them up. So instead of doing all that tediousness by hand, let's open up Excel and let's take a look at what's doing there. Here's Excel. All right. So first I see here, I have the data here. we're going to get the difference. So I'm going to go equals, I'm going to go that cell minus that cell. And I can actually have this here, Excel subtract it all for me. I basically took that corner, dragged it down. Over here, we're going to do equals. And we're going to do the sum. So SUM equals, parenthesis. And highlight that, close parenthesis, and there we go. So negative 19.5. Okay. So that part right there is the sums right there. Now, we want to do the sums, the sum of the differences, summation of the differences, squared. So we want to square that. Okay, so we can also do that Excel too. All right, here's Excel again. So we're going to go equal to. We're going to take that cell. We're going to do a little caret symbol. That little caret symbol is shift number 6. And we're going to square it. And so there is the summation of the differences. Summation of differences squared. Now, if we take a look here, the next part here, we need the summation of the differences squared. Okay, so let's get that here. Let's bring Excel back up. So we're going to take these here equal to, we're going to take that cell where you're going to caret 2. That means we're going to square it. We're going to drag that down. Now all those differences have now been squared. And over here, now we're going to go equal to sum, parenthesis, and we are going to now sum all those square differences. So we end up with 33.33. All right, let's keep going here. Oh, look at that. One more thing here, over here. We can actually divide that by n. That's actually pretty easy to do in Excel too. So let's bring Excel back up. And right now, we're going back to the summation of the differences. We squared that. We're going to divide that by n. Well, what is n? Well, n is right there. N is 13. All right, let's take a look. So over here, I'm going to do that sum squared. And this time I'm going to divide by the n. All right, so over here, equal to that piece there, divide by 13. And there's that value there, 29.25. So now we use Excel to do a lot of the tedious work for us. And now we have some of those values that we can just plug right into that formula. So let's go ahead and do it. Okay, so far in Excel, we have, let's see here, we have this piece here. We have this piece here. And now we can just get this piece. Oh, that's easy. N minus 1. All right, so 13 minus 1 is 12. So that one's pretty easy. So we have that piece too. Now, we can actually have Excel do the rest of this for us, but let's just make sure we have it down here. So we have square root. Now, those values that we had in Excel for the summation of the differences squared was the 33.33. That's going to be minus, and now we got from the summation. Yeah, let's get that back. Sorry about that. So that's the summation of the differences. Taking that, squaring that, divided by the n, we ended up getting that 29.25. And then we're going to take that and divide that by the n minus 1. So that's going to be 13 minus 1. We got that as 12. Okay, so again, we can actually use Excel to get the rest of this for us, or we can plug it in the calculator. But since we're using Excel, let's go and do that real quick. So we are going to do the difference. So we have equal to this guy minus that one. All right, so 4.08. Now, we're going to take that difference and we're dividing that by the n minus 1. And so that's going to be equals that divided by the 12. 0.34. Now careful. It is 0.34, but let's look at the rest of that formula. The rest of that formula had a square root. So that is actually a square root of that 0.34. Now, Excel can do that, or now we can just use our calculators or whichever we want. We just took this really ugly formula, a lot of tedious work. We use Excel to do a ton of it for us, which is great. And I did it in a way that we showed how you were able to see the step-by-step process of how to get each of those pieces. And we're finally left with the square root of 0.34. All right, great. So 0.34, let's just get up a calculator real quick. A simple one is fine. So simple calculator. And we just want the square root of that. So 0.34, root that, and we end up with 0.58309. So 0.5, so this is about 0.58. 583. So about 0.583. So what is that 0.583? So that 0.583 right here is actually that piece. So the SD of this confidence interval. So that's what that is. So now we have that piece. That's actually the more complicated part to get of this all. Now let's get all the other pieces together. So again, we have the SD. So let's actually write that here and then clean it up. So we have the SD is 0.583. All right. So the hardest part is done. Now let's get the other pieces of this. So the other pieces, we need the D bar and we need the T value. Now, of course, we have the end is pretty simple. That's just 13. All right, clean this up. Let's get the other pieces and put this confidence interval together. All right, so now let's get the rest of this. So D bar, we actually have almost all the pieces to get that. Actually, we do have all the pieces to get that, but D bar is equal to the summation of the differences, which we already did in Excel, divided by the n. And the summation, that's a summation symbol, like I try to make a nice Greek letter there. We had that in Excel as 19.5. And that's going to be divided by the n, which is 13. And that, when you divide it, is negative 1.5. Well, let's do that real quick just in case here. All right, so we have 19.5. Oh, 19.5 divided by 13. 1.5. Well, and it's negative 1.5. All right, so we got the D bar. So let's just write that up here. So we got the D bar, negative 1.5. All right, so we got that part. We got that part up there. And let's get the T value. And let's do that. So let's get that T value. So the T value, we have a confidence interval of 90%, giving us an alpha, real bad alpha, sorry, alpha of 0.1. All right, now we need degrees of freedom, n minus 1. So that's going to be 13. Oh, I have 13 minus 1, excuse me, which is 12. So up over here, let's take a look at the t-table. So we're looking at t-table. Looking at the two-tail, 0.1. Again, the table kind of like shows it for us. Degrees of freedom, 12. So we're looking at 1.782. T-value 1.782. So T-value 1.782. All right. So now we have all the pieces for the confidence interval. So we have all the pieces. So let's put that together here. And, well, let's do one more piece right now. This SD here, this S sub D, is divided by the square root of the sample size. So let's do that real quick. So then we have each piece here. All right, so calculator, here it is. So we have 0.583 divided by square root of 13. So divide by 13 root. So we take a look, 0.583 divided by root 13. All right, that's where we end up again, 0.162. So let's do that. Okay, So actually, let's go ahead and finish this up here. So we have this piece here, the SD divided by the square root of n, and let's go ahead and multiply by the t, because remember, this is going to be the exact same on both sides. We're just going to add or subtract it. So let's times that by the 1.782. So times 1.782, and there it is. So 0.2881. So 0.2881. All right, let's grab that. So 0.2881. So we're going to take that and we are going to, where is it? Negative 1.5, negative 1.5 minus, and it's also going to be that negative 1.5 plus the 0.2881. And these are going to give us our values for our interval. And so let's go ahead and get those. So we end up with 1.5 negative 1.5 minus the 0.2881. So that's approximately negative 1.79. Now again, make sure you round to whatever the directions say. I'm just going 2 decimal places here. And then let's go over here to the 1.5 negative plus the 0.2881. And so approximately negative 1.21. So about negative 1.21. And so our interval is going to be from negative 1.79. And it's going to be less than that paired difference, the mean paired difference, less than negative 1.21. And so that is going to be our confidence interval. All right, just 2 more examples here. So this one, now we're going to shift to proportions. So we're going to shift to proportions. For this one, let's see here. Oh, some key things here. Alpha of 0.01. All right. Let's see here. Can you reject the claim that a proportion of 18 to 24-year-olds living in their parents' homes in 2000 was the same for men and women? All right, so we have a claim. So the claim is going to be the same for men and women. Assume the survey included 240 men, 244 women. All right, so that here right there tells us basically what the null hypothesis is and also the claim. So the claim is, are the proportion of 18 to 24-year-olds living at home the same for men and women? And that's also the claim. So the null is our claim here. And so let's take a look at what the null hypothesis and the alternative hypothesis are. And let's, well, let me type this out here. So basically we are looking at the same. So we're looking at equal to versus not equal to. And let's just type that out to make it nice for you. Okay, here you go. Null hypothesis, they're equal. Alternative, not equal. All right, next part. And so just to keep in mind, just remember, this is not equal to. And since it's not equal to, we know that this is going to be two-tailed. And again, now we're doing hypothesis testing. So we're going to take the alpha and we'll divide by 2. And we get, so 0.01 divided by 2, we have 0.005. All right, so from here, we can take a look at the z-tables. All right, so we're looking for the 0.005, 0.005. All right, searching. All right, 0051, 0049. Actually, it is directly in between here. So depending on what the directions say, the directions may say to round, or it may want something exact. And so negative 2.5, let's see here, 7, 5. So that might be what they're looking for. Or, so if it says to round up, you might be going with 2.58, but the exact is negative 2.575. All right, so let's keep going. All right, so that z was a 2.575, or about the 2.58. And so rejection region. All right, now remember, this is symmetrical. So we're looking at the z is going to be less than the negative 2.58, or z is going to be greater than the positive 2.58. All right, let's keep going. Now let's go through and get the p bar. Now what I mean by that is this. So p bar is basically the weighted estimate, and so that's going to be x1 plus x2. And but where do we get that though? That's a good question. Well, I actually just did that. So it was the 0.567 times the 240. All right, so that's going to be the 136. And now the other part here is going to be the 0.442 times the 244. That comes from here, and that's about 108. And that's going to be divided by the 240 plus the 244. So again, what we're doing here is we're getting the, it's called the weighted estimate of the population proportions, the p bar. So we're looking at, we're here, we're pulling those together. That's what we're doing. And what does that end up equaling? Let's take a look here. So we're going to have the 136 plus 108, and that's 244. So 244, and what's that? 240 plus 244 is 484. So we have 244 divided by 484, which ends up to be approximately 0.504. So about 0.504. Well, about 504.1. Let's do that. And so Q, that's a Q bar, is just simply going to be the 1 minus that. All right. And after we subtract it, we get about 49. So about 0.4959. Okay. All right, so we just cleaned it up a little bit here. So we have the P bar and Q bar now. One key thing is to make sure that each of these is above, each of something is above 5. Let me get that typed out for us. So before we move on, the N1 times the P bar and 1 times the Q bar, all of these ones here need to be at least 5. Now, we're going to go, I'll just do it quickly here, but we have 440 men, 244 women. When we multiply by these guys, it is going to obviously be well more than 5, all of them. But let's just, just for argument's sake, let's show you. So 0.5041 times 240 is 120, and 244 times the 0.5041 is 123. And as we go through each of these, now as you're working through some homework problems, or it might ask you to go through each of the steps and verify all of those and give the exact numbers. But each of them, as we go through, you'll see is definitely at least 5. So that's one thing you do want to verify. So now at this point, I'm going to actually use some technology here. I'll take an online calculator here, and I have already entered here. So I did 240, 244. We entered the information, calculated it. Now we ended up getting a z-score of 2.7, about 2.76. So what does that mean? Well, let's go back over here. 2.76. So we have 2.76 2.76. I use an online calculator to get that test statistic. So what does this mean? 2.76. Well, this would be over here in that rejection region. So in this situation, what we have is the test statistic is in the rejection region. And since it is in the rejection region, we have enough evidence to reject the claim. Now, the claim here was that the between the men and women let's see, the proportion of 18 to 24-year-olds living in their parents' homes in 2000 was the same for men and women. And so since we have the 2.76, and that's in the rejection area, we reject that claim. We rejected the null hypothesis. Okay. And again, we used a little bit extra technology in there to do some of our tedious work. But let's do a proportion here using a confidence interval. Or to calculate a confidence interval, let's take a look at one last example. All right, so here we go. We have this example here. We have a survey of students taking a standardized test, and it revealed that 9.6% of students were planning on studying engineering in college. In that survey of that many students taking the SAT, 9.2% of the students were planning to study engineering. So we want to construct a 95% confidence interval for the difference between the proportions. All right, and so let's go step by step. Well, we first have to know what p hat is. All right, that's p little hat, little caret, little hat. And so we can easily get that. And remember, p hat 1, p hat 2, that just represents the number of successes, the proportion of successes. And that's actually already given to us right there, 0.96. And so let's highlight that. So this 0.96, that's p hat 1. And the second one is right here, 9.2. And so that's p hat 1 and p hat 2. Pretty simple. All right, so as you can tell here, stuff is going to come together very, very quickly for this question. So the next part, we got to get the Q hats. And well, that's really simple. That's just one. Oh, I got the highlighter on. 1 minus that 0.096, as well as the 1 minus the 0.092. So when you see I see Q1 hat, Q2 hat, that's basically just taking these and we're subtracting them. That's all that is. And we can do that pretty quickly here. So 1 minus 0.096, 0.904. And over here, 1 minus 0.092, and that's 0.908. And if we look here right away, we already have this item. We have this item. We have this. We have this. We have the N1. We have the N2. All right. That makes this actually pretty easy. It makes it really easy if you think about it. So over here, on this other side, we notice we have exactly the same thing. So we have exactly the same thing on both sides. So what I mean by both sides is both sides of this guy right here. So we're trying to find that confidence interval of what that would fall in between. So we have everything except that z. So let's go ahead and look for that. So confidence interval 95%. So that's going to give us, so then again we're getting the z. So we're getting alpha is 0.05. So alpha 0.05. And remember, this is a confidence interval, so alpha divided by 2 is going to be the 0.025. And now that should be, again, going through everything, we start memorizing what those z values are. And at finding 0.025 in that z table, you'll find that it's 1.96. 1.96. But just to make sure, 1.96, there it is. All right. So now we have that z. So now we have all the various pieces. But we can actually do some of these right in the calculator. So it kind of makes things a little less cumbersome to try to write it all out. So let's put it in that calculator. We can actually even put it in, pretty close to one step, or just to make things not as confusing. But we got the z value, 1.96. So let's get this side here. So 1.96 times, now we have a square root, and we can do a bunch of different grouping symbols here. So let's group that, P1 and Q1. So P1 was the 0.096 times 0.904, 0.904, and that's divided by the N1. Well, N1, that's a big N1 right there. 1,068,000. Let's make sure we got all that. 1,068,000. Okay. All right, so that's that first part there. We add parenthesis, and let's get that part in. So we're at 0.092, and that's going to be times 0.908 divided by N2, which is another fairly large number, 1,476,000. Close those up. All right, so that's going to get us this whole entire side here. So let's do it. I know the answer looks weird, but this here is the same thing as saying about 0.0000727. So we'll leave it at that. So something about that. Because remember, this here, we're going to be subtracting some pretty small numbers from it. And what I mean by that is this. The p hat 1 minus the p hat 2, well, what exactly is that? Well, let's take a look. The p hat 1 is 0.096 minus 0.092. So we're basically going 0.004, and we're going to subtract that 0.0007. And we're going to take that 0.004, and we're going to add the 0.0007. Now, most often you'll see rounds in there's 2 decimals, 3 decimals. But so this one here, if we subtract it, we're going to get 0.0033. And over here, we're going to get 0.0047. Now, if the software, if the directions ask you to round to the nearest 3 decimals, this one would be about 0.003. And this one would be about 0.005. All right, so that's most likely what something like this, a question would ask you. Most likely 3 decimal points, 2 decimals, depending on, again, the question. So the interval would be from 0.003 to 0.005. So let's see if I can get that more formally written here for you. And there you go. So the confidence interval between for the difference between the two proportions is 0.003, difference of the proportions, to 0.005. So now we're looking at the differences of those very small percentages. And so that's why these decimals end up to be pretty stinking small. All right, so that was the last example for this particular chapter. Now I went over a lot of these in detail because there's quite a few calculations that I wanted to make sure you saw. And I want to give you a good variety. But if you do have any questions, I'm here for you. Remember, I'm here for you, and keep an eye out and watch those other posted videos for the individual assignments. And please do not hesitate to ask for any assistance. I do see emails and text messages much more quickly than posts in the eClassroom. Also, there is tutoring available for you. Go to course menu, course dashboard, IW resources. It's there. It's an upgraded service for you guys. We want to make sure you have all the resources possible to succeed. And also, I do have live office hours. Make sure to check the workshop announcements for more details. I just want to make sure that you know that IW has your back, and we're here for you. Hope you have a blessed week.